Hello and welcome to my talk. I'll present DeepCoMP, which is our approach for multi-cell selection in 5G and beyond using reinforcement learning. I'm Stefan Schneider, and this is joint work together with colleagues from Paderborn University and from Huawei, Germany. So in this joint research project, we used Ray RLlib to implement, deploy, and evaluate our prototypes, but more on that later. For now, let's start with the scenario and the motivation of this work. So we're here in a use case where we consider a wireless mobile scenario where we have dense and partially overlapping cells. So here indicated by these antennas, and the circles indicate the rough range of these cells. And then we have users moving around these cells represented by these smartphones here. And these users want services like AR, VR, cloud gaming, video streaming, all things that require high and reliable data rates. And one option or one way to achieve such high and reliable data rates is using coordinated multipoint, or short COMP. And here we focus on COMP coordinated scheduling and joint transmission, where users can connect to not just a single cell, but to multiple cells at once, and then receive data from these multiple cells simultaneously, such that their effectively received data rate is significantly increased. And so as these users move around and connect to the different cells, they of course compete for limited radio resources, for example, in the form of radio resource blocks, which are limited in frequency and time domain. And here we explicitly don't make any assumptions about how these cells allocate resources to connected users, because this might be vendor specific or proprietary, and it might very well happen that cell A here has a different resource allocation scheme than cell B and cell C. So we don't need to know about these resource allocation schemes. We don't assume that they're homogeneous. And so in this whole scenario, our goal is to optimize dynamic multi-cell selection. So for each user over time, we want to decide how many cells each user should connect to and which cells it should connect to. And the goal here is to maximize the total quality of experience, or here short QoE, of all of our users. And we model this quality of experience based on some previous studies as a logarithmic function of the data rate for each user. So if the data rate is 0, then the quality of experience is really bad because the service does not work. And so if we increase the data rate by just a little bit, then the quality of experience dramatically improves because this service suddenly starts to work. But then if we increase the data rate more and more, at some point we get diminishing returns. And one nice thing about this utility function is that it implicitly encourages fairness, because if we want to maximize the total quality of experience for all of our users, we can do this most effectively by improving the data rate of users that currently have a low data rate and low quality of experience, because then we get this huge gain in QoE, whereas improving the data rate of users that already have a high rate is not so helpful here. But as I said, this is all based on previous studies, but it's just an example. We could also easily optimize any other utility function here. So our goal is to maximize this total quality of experience, and we want to do this with deep reinforcement learning. And for that, we proposed 3 different approaches. The first one is called DeepCoMP, and it's a centralized approach. So we have a centralized training procedure, and we do inference in a centralized way. Then we have 2 multi-agent approaches. D3CoMP is completely distributed, so it uses distributed separate policies, separate neural networks during training and also during inference. Whereas DDCoMP is also multi-agent, but it uses a shared policy, a shared neural network during training, which can then be replicated for distributed inference. So I'll walk through these different approaches and compare their strengths and weaknesses. Let's start with DeepCoMP, the centralized approach. DeepCoMP requires a global view and global control of all of our users in the area. So this is a bit challenging from a technical perspective, and it also means that we get a large observation and large action space if we have many users. So quite high complexity and training effort, which is a bit of the downside of this approach. But on the upside, it can learn really powerful and fine-grained coordination and cell selection policies where the different users cooperate with each other, because it does observe and can simultaneously control all of the users together. So to implement DeepCoMP, we need to define and design the Markov decision process, or actually partially observable Markov decision process. And we defined observations for that based on the current connections of each user to the different cells. based on the signal strength between the different cells and users. So this is the signal to interference and noise ratio, or short SINR, and based on the user's current quality of experience. And here we don't even need to know this utility function that I showed earlier. We simply need to approximate or estimate the instantaneous quality of experience for each user, and there are approaches out there to do that. So given such an observation, our DeepCoMP agent makes an action, and that action defines the cell selection for all of our different users. And kind of the default action that we have here is to simply keep all connections as they currently are. So not connecting to any new cell and also not disconnecting from any cell. But of course, the agent can also decide that a user should connect to a new cell or should disconnect from an existing cell or from a connected cell. And we designed the action space here in a way that each user can make at most one connection or disconnection per time step, simply to limit protocol overhead. And so with these observations and actions, the agent, after each action, receives a reward, which we define to simply be the sum of all users' quality of experience, because that's exactly what we want to optimize. So that's the centralized DeepCoMP approach. Now the question is, how can we move from the centralized approach to the distributed approaches? And for that, we need to make some adjustments. So the main idea is that rather than one centralized agent that observes and controls everything, we have separate DRL agents, one for each user. And each DRL agent only has local observations of what the own user does and only controls the cell selection locally of this own user. And that's, of course, a lot simpler. We have a much smaller observation and action space. It's easier to implement and it's a lot faster to train. So that's really great. But there's also a downside or a challenging part to it, which is that such an approach is quite prone to learning greedy behavior. So if an agent only observes their own user, only controls the action or the cell selections of the own user, trying to maximize the quality of experience of only the own user, of course it learns a policy that greedily maximizes the own user's quality of experience. And this often means that these policies are quite unfair and really don't optimize our total quality of experience. And that's what we want as an objective here. And so we need to make some adjustments. And first of all, clearly here the observations and actions are defined per user for a single user, corresponding to the agent, so not for all users like in the centralized approach. But we also need some extra observation to make these agents aware of what's happening around them. And for that, we introduce one extra observation that indicates the number of users per cell. And that helps these agents to recognize if a cell is currently unused and available, or if a cell is highly congested, and then helps avoid congested cells. We also need to adjust our reward to not just consider the quality of experience of our own user or of each agent's own user. And here in this distributed setting, we can't simply sum up over all users' quality of experience because we don't know them. But what we can do is we can average, or sum up, in this case average, over the competing set. And we define this competing set as all users that are connected to some of the same base stations or to some of the same cells as our own user. And here we assume that via these connected or shared cells, we can exchange the quality of experience of these users. And so by using this average QoE over the competing set, we can avoid greedily maximizing only our own users' quality of experience. And that helps encourage agents to use free cells and to avoid competition with other users. Or if competition is necessary, then rather compete with users that already have a high quality of experience where this competition is not as harmful. So based on this adjusted POMDP, we designed and developed our two distributed approaches. First, DeepCoMP, which is fully distributed, where we have these independent DRL agents, each with its own separate policy and neural network. And during training, we don't need any extra communication for these DRL agents because they are all trained independently. And one benefit here is that because they all have their own policy that's being trained independently, they can potentially learn heterogeneous cell selection policies, which might be useful if our users are very different from each other. Then we also have DeepCoMP, which is also a multi-agent approach. It also relies on local observations and actions. But here, these agents, at least during training, use a shared policy, a shared neural network, and combine all of their and all the agents combine their experience during training such that we have more data that we can leverage during training from all the different users. And it also means that we can often learn better and slightly more robust policies than with DeepCoMP. And so overall, these are the three different approaches that we propose: the centralized DeepCoMP approach, then the fully distributed DeepCoMP approach, where we have separate policies for each agent, and then the DDCoMP approach, where we have a centralized training procedure with a shared policy. And then during the production deployment, we can replicate this policy, replicate the neural network, and still perform inference in a distributed manner. So now that we have defined our problem, we have designed our three different approaches, we need to go and implement them. And that's exactly where Ray RLlib comes into play. So as a first part of the implementation, I implemented the custom and configurable mobile environment that I used for training and for evaluation of these DRL approaches. And of course, I had to implement this OpenAI gym interface here such that I could connect different RL approaches to this environment. So for a single agent, for the centralized approach, this DeepCoMP approach, the code could look somewhat like this. It's a bit of a simplification here, but the real code is on GitHub. So here I import gym and I implement a gym, or I inherit the gym environment, and I implement a class mobile environment that has a constructor, get some configuration dict here. And then it has these typical reset, step, and render functions that are dictated by the gym interface. And I also have some functions to get the current observation and current reward, which are used inside the step function. And the step function also implements all the dynamics and all the environment logic. Now the question is how to get from this single agent approach or single agent environment to a multi-agent environment. And here Ray RLlib helps a lot. And that's actually the main reason why I switched to Ray RLlib in the first place, because initially I was using a different framework which did not support multi-agent. But with RLlib, what I had to do is simply import from Ray RLlib the multi-agent environment, and then create a new class where I inherit, first of all, from my single agent mobile environment and then this multi-agent environment. And I only had to override here the constructor to define this adjusted observation and action space, and then also implement and override the get observation and get reward function to also make the adjustments here. But for example, I could simply use the reset, the step, and the render functions, which implement all the main logic of this environment. What's also very handy is that RLlib supports gym dict spaces, so I can define my observations here simply as I dict, so combining a multi-binary observation space for the connected observation, and then a continuous box space and another continuous box space for the other observations, which is really useful and simple to do, but it's not supported by many other frameworks. So that's also a nice extra here. So now that the environment is implemented, I of course also have to implement now the RL agents. And here I chose the PPO implementation, which comes with Ray RLlib. So that's again very nice that there are so many high quality implementations of different RL algorithms. And I chose the TensorFlow 2 version, but there are also PyTorch versions. And as I said, for me, the main reason to switch to RLlib was this great support for moving from the centralized approach to the multi-agent approach. And that's not just true for the environment, but also for configuration and training of these agents. So a bit oversimplified here, when configuring the single agent, the centralized approach, I simply set in the configuration the multi-agent option to be empty, more or less, so I don't define any multi-agent policies here. And then if I want to go to a multi-agent approach, and for now let's look at the DeepCoMP approach where I have separate policies for each agent. I simply have to set the policy. So here I want to have separate policies for each agent. So I iterate over all my different agents. And for each agent, I create a separate policy based on the observation and action space here. And I then also have to define the policy mapping function. And in this mapping function, I simply assign a separate policy for each agent based on the ID. It's also very simple to configure this DDCoMP approach where I have a shared policy, at least during training. And here, instead of iterating over all agents, I simply define a single policy that I called shared, but I could call it any other. I could use any other name here. And then in the policy mapping function, I map each agent to the shared policy such that all agents use the same policy. And you can imagine that it's also very easy to do something hybrid here, such that some agents use a shared policy, some agents have their own policy, and that's really easy to configure here. And configuration and training is easy. Also, inference is quite easy. In this single agent case, This is the kind of typical approach that you have, where you get the environment, you reset it, get the initial observation, and then loop until the episode is done. And in each step, you pass the observation to your centralized or to your single agent. The agent computes an action. That action is passed and applied to the environment, and then you get the next observation reward until the episode is done. Now, moving from this centralized single agent inference to multi-agent inference is also quite simple. So not much more code here. I again start with the environment being resetted and loop until the episode is done. But here the action and the observation are not a single observation action, but they're dicts because I have now actions and observations for each agent. And for that reason, I iterate through these observations. And for each agent, I get the corresponding policy using this policy mapping function here. And that's nice because now I don't have at this point to distinguish between the DDCoMP and the D3CoMP approach, because that's already defined here in the policy mapping function. And so I get the policy, whether it's not a shared policy or a different policy for each agent. And I then get the action from each agent based on the agent's observation and based on the selected policy. And then once I have collected all the actions, I can pass them through the environment and then make the next step here. So as I said, this support for multi-agent was for me the biggest reason to switch to RLlib, but there are a lot of other nice features and benefits. So for example, this full integration with Tensorboard, where there are lots of useful metrics supported by default that are great for monitoring training progress, also for debugging or for improving these approaches. It's quite simple to implement own custom metrics. So for example, you can add a metric for each step in the episode or a metric just on the at the end of each episode. And I used such a custom callback to keep track of the total quality of experience, which is what I wanted to optimize. So I added a custom metric here. One of the great things with Ray is that it's easy to go from local development, either Linux or Windows, to cluster deployment. In my case, I deployed these agent or trained them on the university's local private cluster, which was really useful to speeding up evaluation and scaling and running lots of things in parallel. And lastly, I have to say thanks for the great support from the Ray or from the Anyscale team, and also from the very active community. So whenever I had a question or hit a wall, I could ask on Slack, on GitHub, or on the Discuss forum. I would always get useful tips and advice on how to continue, and that was really useful. So thank you. Okay, so the implementation is done. We have our environment, we have our agents. Now, of course, the question is, does any of this really work? And for that, let's start with an untrained agent. So an agent that's still initially randomly initialized, so it starts with random actions. And what you'll see here is that this, of course, does not work well at all. So here we have the centralized DeepCoMP approach that's trained for 200 steps. So this counts as not trained at all because it's so little training. And we have 7 different cells here indicated by these antennas. And each of these larger circles indicates the rough range here. And then we have the small points or circles with the different colors that move around. And these represent the different users. And the color represents the current quality of experience of these users, where red is really bad. So most of our users are very, very unhappy because they're not connected to any cell. And just some of these users are by chance connected to some cell in range, and for some reason always or often directly disconnected again. And so overall, with these random actions, of course, we get a horrible cell selection policy. The average QoE for all of our users is really, really low and unstable. And that's a bad starting point. But if we just train for a while, here for 2 million time steps, then you can see that the agent really learns a very useful cell selection policy. So now all of our users are connected. We have very smooth handovers between the different cells. The agent learns to use comp here at the cell edge where it's really useful, but it doesn't use it excessively to avoid unnecessary competition. And all of this was learned without any human instruction or so. And the average QoE here is in the end a lot higher than in the beginning, quite good and very stable. And so overall, our DRL approaches learn multi-cell selection very effectively, and they don't need any human intervention or instruction or expert knowledge. I think that's a big advantage over existing approaches. Of course, We also did more systematic experiments and evaluation. So we varied the resource allocation schemes, the number of users, the number of cells, the distance between these cells. And in each of these scenarios, we simply retrained our agents, but we did not give them any extra information, no extra instructions, no expert knowledge. And they just trained and learned to adapt to these different scenarios. And in each of these scenarios, our 3 DRL approaches outperformed other existing approaches here. And the two multi-agent approaches are quite similar in terms of performance, but the centralized DeepCoMP approach is quite a bit better than the two distributed approaches, simply because it does have this global view and control of all users, and it's very close to optimal here. And so overall, the DRL agents learn to self-adapt to each given scenario, and they outperform existing approaches. Now, you might be wondering, why do we even bother with these distributed approaches if they're always worse than the centralized approach? And the reason is scalability. So if we look at scenarios with more and more users, the action and observation space of the centralized DeepCoMP approach grows and grows, and the complexity grows, and the training and the conversion times also grows. Whereas for the distributed approaches, for example here DeepCoMP, the observation and action space is completely invariant from the number of users. And so in this example here, DeepCoMP converges within here 200,000 training steps, more or less. Whereas the centralized DeepCoMP approach needs much longer. It needs more than 1 million training steps to reach a similar performance, so more than 5 times as long. And that's a huge benefit and advantage of these distributed approaches. But if we keep on training and train for long enough, ultimately the centralized approach learns a slightly better policy than the distributed approaches, simply because it does have this global and centralized view and control of all users. And so overall, our distributed DRL approaches learn good cell selection policies really quickly, whereas the centralized approach needs some longer time to train, but then ultimately learns a policy that's slightly better. And both of these approaches, or actually all 3 of them, outperform existing approaches. Yeah, and that already brings me to my conclusion. So I presented our 3 different self-learning DRL approaches. First of all, the centralized DeepCoMP approach that's a bit slow to train, but ultimately learns highly optimized cell selection policies. So this is really useful for quite stable environments with not too many users. And then the distributed DeepCoMP and D3CoMP approach are trained a lot faster, and they make fast local multi-cell selection decisions. And those approaches are really useful for more practical scenarios with large scale, many users, or faster fluctuations. We developed and deployed all of these approaches, all 3 of them, with Ray RLlib. And here, as I said, really great was the support for multi-agent, but also all the other features were really helpful here. And ultimately, we found that these 3 approaches outperform existing approaches. They work with minimal realistically available information. They self-adapt to varying different scenarios. They're robust to sudden change, and they scale to large networks. And so I believe that these approaches, that this work is an important step towards self-adaptive and effective coordinated multipoint in practice, and towards higher quality of experience in 5G and beyond. So that's it. Thank you for your attention. If you're interested, feel free to check out the code that's publicly available on GitHub. Thank you.